So in this first lecture for this week, we'll introduce two very basic problems in statistics, namely that of hypothesis testing and estimation. Okay, so essentially the entire statistics is about roughly about these two problems. So there's no way I can describe them completely in this single lecture, which is just 20 minutes. Perhaps it will be just about 20 minutes long. But I want to give you some basic idea about these problems, because it is through this problem that we'll be able to characterize how much information does some random variable y contains about another random variable x. So let's begin. Right. So let x and y be two random variables, two jointly distributed random variables with joint distribution pxy. So this is the notation which we'll use throughout. So p subscript xy. So this is the joint distribution of x and y. Okay. Suppose that x is an unknown random variable and y is the observed random variable. You can think of some example where x corresponds to some binary random variable like a class, and y corresponds to something that you see about it. So for a very concrete example, which is quite popular, which is quite important in practice, you can think of the problem where you want to predict if a particular user will click your advertisement or not. Okay, in that case, there are two kind of users: the users who click and users who do not click. And this is your unknown random variable x. You don't know which user is which. So when x is 0, then this corresponds to a user who doesn't click, and when x is 1, it corresponds to a user who will click. And y can be features of this user. For instance, which country is the user logging in from? Where did it come to your website? From which other website did it come to your website? What are the other things you know about the user from the user's cookies, and so on and so forth? What time zone the user in? Sometimes you have much more information. There are several competitions on a website like Kaggle, which ask you to solve this particular hypothesis testing problem. Okay, so x is the unknown, and y is the observed random variable. Okay. So before we proceed, we have to put down some basic notation. So we have to bring in this notion of conditional distribution, p of y given x. Okay, it's a distribution of y once you condition it on x. Okay. So remember, x is your unknown and y is your observed random variable. This distribution has a special name in information theory. It's often called a channel. Okay. So we just this is called a channel. It may sound like a strange name to you, but perhaps I'll try to explain why this is called a channel. So x is the thing that you don't know, and it's the message that you want to figure out, and y is the observation that you have. And this x is passed through some channel, this particular channel, to give you y. So this channel is thought of like some communication channel, and you observe x through it to see your y. Okay. So from now on, we'll call this conditional distribution a channel, which adds some noise to the input to give you the output. All right. A simple way to think of a channel is that it is a randomized mapping from this input alphabet x to this output alphabet y. Okay. So corresponding to each x, there's a distribution on y, which we can abbreviate by w subscript x. Okay. For discrete random variables, to describe this distribution w subscript x, we only need to give its PMF, probability mass function, and most of this course will be about discrete random variables. So for discrete x and y, we will use this notation w of y given x. Okay, this w of y given x here. It will denote the probability of y equal to y given that x is equal to x. It's that conditional probability. So just to be explicit here, this is by base rule. This is equal to probability of y equal to y, x equals to x. Maybe I should make some more space for myself. All right. So this here, just by base rule, is the probability y equal to y, x equals to x divided by probability x equals to x. This is the conditional probability. This is valid as long as the probability of x equal to x is non-zero. Okay. All right. So this conditional distribution is what we'll call a channel. Now, so when we observe a y and we want to infer something about x. Okay, then we have a channel associated with y, and we can think of this family of this family of distributions w subscript x for different x in x as representing the experiment that we are running to determine the unknown x. Okay, and in this experiment y is the observed random variable and x is the unknown random variable. Okay, once again, the goal is to determine x by observing y, which is distributed. This notation, this sim we'll use for distributed, so which is distributed as wx. This is a classic statistical inference problem. All right, that's what people in statistics want to do. They want to figure out what is x by looking at y, where the distribution of y depends on x, and this channel essentially represents that dependence. So we will look at a specific kind of statistical problem, which is sometimes called Bayesian, which is sometimes called a Bayesian formulation. So what happens in a Bayesian formulation is that you have a distribution which generates this x. So we assume that x is generated from a fixed distribution px. That's what we'll assume throughout. And such a formulation is called a Bayesian formulation. So in this part of the course, we will go with a Bayesian formulation. So let's take a very concrete example. Let me introduce what is called binary hypothesis testing. So binary hypothesis testing is a problem, is a statistical problem when this x, the unknown x, has cardinality 2, just like a click prediction example that I described. So there are two hypotheses. This is my calligraphic H. So there are two hypotheses, H0 and H1. Under H0, your y has distribution W0. Under H1, your y has distribution W1. And your goal is that upon observing y, which has distribution Wx, and this x itself is random, we want to figure out what x was. So what we can do is we can form an estimate x hat of the unknown x by looking at y. Okay, and how do we know that this is a good estimate? Well, what we want to do is we want to minimize the average probability of error. So how is this average probability of error defined? We want to minimize the probability that x is not equal to this x hat that you have formed. So what is this probability of error? Well, we can write the total probability formula. So how does it go? Probability that x is equal to 0, okay, multiplied with the probability that the output x hat is different from x, given that x equal to 0. This will happen when g of y is 1. Okay, so when g of y is 1, the output will be 1, while input was only 0. So this is for the first part of that error probability. Px0 multiplied with probability that gy equals to 1 given x equal to 0. Okay, so that's the distribution here. Maybe I should write it more elaborately. So this is basically probability that gy equals to 1 given x equals to 0. Okay, plus probability that x equal to 1 multiplied with probability that gy equal to 0 given x equal to 1. So the probability that you declared 0 given that the x was 1, and probability that you declared 1 given that x equal to 0. This is the probability of error. So if this mapping G is deterministic, okay, if it's a fixed mapping which doesn't use any extra local coins, so what is this notion of deterministic mapping versus randomized mapping? Well, in statistics, it is common, statistics and algorithms, it is common to think of randomized mapping, where the mapping G is not only a function of your Y, but also an independent coin which you can generate in your computer and use to make a decision. Okay, but for simplicity, we just look at simple functions, simple mappings, which are deterministic. So they just look at Y and declare 1. So for such a mapping, we can think of a set A0 as a set of those Y's for which G of Y is 0. Right? We can always define this set A0. It's a set of those Y for which this mapping G declares 0. So what is the probability of error in terms of this set A0? Well, it can be written as P of x0. Now under x equal to 0, the distribution of Y is W0. What is the probability that you don't see a Y in A0? Well, that's this probability that Y is in A0 complement, plus probability that X was 1 and you saw a Y in A0. But this time the measure that you use is W1. The probability that you use is W1. Here you use the probability W0. It's a more detailed expression for probability of error. Okay. So the distribution Px has a name. It's called a prior. And so whenever you may have already heard this phrase prior, it's your prior belief about the unknown x, okay, or about the unknown hypothesis. So it's called prior. It's your prior belief before you saw y. Okay. The distribution p of x given y is the posterior distribution. It's a distribution of x after you have seen y. Okay. Alright, and this posterior distribution can be computed using Bayes rule. It can be written as this: W of x given y is W x given P of x given y is just Px W of y given x. This is the conditional distribution by Py of y. Okay. So when you have an input distribution, the prior Px and this channel W, you can also write the output distribution. So I'm calling it the output distribution for the output of the channel. The input distribution is prior. Output distribution is Py, the distribution of the observed output. It's given by the average distribution, where the averaging is done over this Px, your prior. Okay, so we're given each x, the distribution of y is Wy given x, and you weigh this distribution by Px. Okay. So for a uniform prior, in this particular case, a uniform prior corresponds to having equal belief about both 0 and 1 to begin with. Okay, so you have no preference of two hypotheses. You have no other information to prefer one over the other. So Px0 equals to Px1 equals to half. That's a uniform prior. Okay. For this prior, the probability of error can be expressed as half times probability under W0 of A0 complement plus half times probability under W1 of A0. So this half corresponds to x being 0, and under x being 0, the distribution of y is under W0, and this corresponds to you declaring 1. This set A0, remember, corresponds to your rule gy. And again, with probability half, x is 1, and then when x is 1, then the probability distribution y is W1, and this corresponds to you declaring 0. So this is the probability of error in terms of the set A0. Since W0 of A0 complement is 1 minus W0 of A0, if you substitute this, okay, if you substitute this here, you get half minus half into this. Remember, now A0 is the same set used in both these measures. So can you recognize this expression? Somehow, what can we do with this? Okay, let's see what this expression is about. I think you have seen this expression before in this course. Alright, so note that we can choose any A0 because we are looking for the best decision rule. So we can choose any A0. Each mapping G, which is our decision rule, corresponds to an A0. The probability, the least probability of error, which we'll denote by PE star uniform, this uniform is for the uniform prior that we choose, is given by this quantity here. PE star is half minus half into, since you want to minimize probability of error, you'll maximize this thing which is negative, max over AW0, A minus W1A. Alright. So can you now recognize this quantity? Is it something that you have seen before in this course? Why don't you pause and think about it? Indeed, this is a total variation distance. So the probability of error is the total variation distance between W0 and W1, and therefore the probability of error is half into 1 minus total variation distance between W0 and W1. And the best rule which attains this minimum probability of error is the same as the set A which attains this total variation distance. And if you remember, this set A is given by a set of those y for which W0y is greater than W1y. So this is something very interesting. We have given an explicit formula for minimum probability of error under uniform prior, and this formula entails the total variation distance, some quantity we saw earlier. It allows us to specify the optimal test, the one which minimizes this probability of error under uniform prior, and that's a very natural test. Whenever we see a y which is better explained by W0 than W1, in other words, which has higher probability under W0 than W1, then we declare 0. And whenever we see a y which has higher probability under W1 than W0, then we declare 1. This is the rule. Furthermore, this particular probability of error formula here says something very nice and heuristic. Okay. It says that this probability of error P star, it is large when the distance between W0 and W1 is small. So hypotheses which are close to each other are harder to distinguish. Okay, this is very much like Euclidean geometry or our day-to-day life, when we know that if you want to understand the difference between two phenomena which are very close to each other, okay, then it will take a greater effort. For instance, if you want to measure a very small distance, the width of your hair, for instance, it will take a very fine scale. It will take a greater effort. Similarly, to distinguish if your underlying hypothesis were W0 and W1, it will take greater effort if W0 and W1 were close in total variation distance. So this heuristic is some very basic heuristics about heuristic about statistic, and I would require you to I will request you to go back and think about it and try to remember it throughout this course. Hypotheses which are close to each other in total variation distance are harder to distinguish because its probability of error under uniform prior is larger. Okay. So some terminology. This function g is called a test because it tests if your hypothesis was 0 or 1 by looking at y. And the function g star y, which is just this function corresponding to this a star, this one declares 0 if w0 is less than w1 and otherwise it declares 1, is a Bayes optimal test, or sometimes it's just called Bayes. Okay, so it's a Bayes optimal test, and this particular test is optimal for uniform prior because that's the one for which we got this answer. So it's called a Bayes optimal test, optimal for a uniform prior. All right. So this was one kind of hypothesis testing problem where you had two hypotheses, x hat cardinality 2. Next, we can look at what is called the Emery hypothesis testing problem. This M here is a number, just like binary. I'm just calling it Emery hypothesis testing problem, where the cardinality of this set x, the unknown x, is M. And you form a test G which looks at y and outputs x. Okay, this is again a test. So it looks at y and tests to decide which of the x was true. So it gives out an x hat. And probability of error can again be defined as probability that x hat is not equal to x. And the optimal test is the one which minimizes this probability of error. We'll come to analyzing Emery hypothesis testing later, but I just wanted to formulate the Emery hypothesis testing problem. Just like we have a binary hypothesis testing problem, we have an Emery hypothesis testing problem. So to think of an example of this problem, you can think of basic digital communication. Think of modulation schemes, amplitude modulation scheme or QPSK scheme, where you send a symbol and the symbol gets corrupted by noise. And that's what you observe. And by looking at it, this noisy version of the symbol, you would like to recover the symbol back. What was the symbol that was sent? Now, in this case, the unknown hypothesis, the unknown hypothesis class is this set of all different symbols that you could have sent. And this M corresponds to a number of different symbols in your constellation. Okay, for instance, 16 QAM used in, let's say, used popularly in LT, will have 16 symbols. And you observe y, which is a noisy version of the symbol sent, and you would like to determine which symbol was sent. Okay, that's an Emery hypothesis testing problem. So we saw a binary hypothesis testing problem and an Emery hypothesis testing problem. And we looked at Bayesian versions of this problem where a distribution was put on x, the unknown x. Okay. So hypothesis testing is one kind of statistical problem where you have a hypothesis and you observe some random variable whose distribution depends on the unknown hypothesis, and you want to determine the unknown hypothesis, and you impose a probability of error criterion, and the goodness of your test, the so-called test, will be determined by how small the probability of error is. Another kind of problem looked at in statistics is what is called the estimation problem. For estimation problem, x need not be a discrete random variable. The set x need not be discrete. It can be continuous, but for simplicity, we'll just mostly look at a discrete x. So you note that this criterion here that we were looking at for our hypothesis testing problem, probability that x hat is not equal to x, you can view this as probability under pxy of indicator function, expectation under pxy of indicator function, x hat not equal to x. Remember, this x hat is a function of y. Alright. For a general x, we can consider an arbitrary loss function. This can be thought of as a loss function. This is the loss that you incur when you declare x hat instead of x. And this is the expected loss. But why are we considering only this indicator function as loss function. This indicator function is very well suited for hypothesis testing, but in general, we can consider some other loss function. So, what is a loss function? Like here is a generic interpretation of a loss function. When your true hypothesis is x, or your true unknown x, the unknown x is x, but you declared some x prime, then you incur a loss which is L of x prime. Okay, so it's a positive. All we are telling about this is it's a non-negative number, and we are interested in expected loss. This capital L under rule G and averaged using px, and it's given by this. Okay, it's the expected value of loss between gy, that's what you declare, and x, the input that you have. Okay, yeah, this is small notation I use. Typically, loss functions that we will encounter in this course are symmetric. L of gyx equals to L of xgy, but here, just for convention, I am putting the output gy first and then the unknown x. So what is the optimal loss? What is the minimum loss? Well, it's the one which is minimized by all your allowed tests or all your allowed estimates g. Now I should think of g as some estimate of x that I form by looking at y. So in this case, a good example of this problem is what is called the regression problem. So you observe one quantity like temperature in Bangalore, and from that you want to predict another quantity or estimate another quantity like temperature in Mysore. Okay, or many other such things, and they will fall in the category of an estimation problem. And we are looking for the best rule G, which minimizes this loss function. So this minimum loss function is what we call L star of Px, and this Px is the distribution of the unknown x. So we assume for now that this Px is fixed. A popular loss function for d-dimensional vectors, so when x equals to Rd, is this Euclidean loss function, which is just the Euclidean distance square. It's called the mean square loss. It is summation I equal to 1 to d, the distance, the difference of xi minus x prime I whole square. Just the distance squared between these 2 points. Okay. So this LGPX is called the mean squared loss. Okay. And the quantity L star Px in this case is called the, so what is L star Px? It's the minimum error that can be incurred when you measure loss according to this. So in this case, this error has a very popular name. It's called the minimum mean square error, MMSC, and we often look for estimates which are MMSC estimates, the estimates which minimize this mean square error. All right. So to conclude this video, we have seen three different statistical problems. The first one was that of binary hypothesis testing, where there were two unknown values of x, 0 or 1. At hypothesis 0 and hypothesis 1, and you observe a y which under 0 had a distribution w0 and under 1 had a distribution w1, and we wanted to figure out if the unknown x was 0 or 1. This is binary hypothesis testing problem because x can take two values. We also quickly defined this generalization to Emery hypothesis testing problem, where the unknown x can take m values. This m can be 16, some number basically. Okay. And then finally, we looked at a statistical problem of estimation, where the unknown x can take perhaps not even discrete many values, but continuously many values. And the goal is to estimate x by looking at y. And we define it, and the goodness of our estimate will be determined by a loss function. A popular loss function, for example, is the mean squared error loss function. In all these formulations, we were always putting a distribution on x, which we were denoting as px. This is the prior that we put on the unknown, right? In the next lecture, I'll give you some more concrete examples of these statistical problems.